In this video, I want to talk about one of the most important and widely used features in the ISE software. With this capability, you can significantly speed up the implementation process for your systems and, of course, save on costs. The ISE software offers a variety of tools to help you accelerate the implementation process. One of these features is the ability to use IPs or modules that are pre-designed and ready for you to incorporate into your projects. IP, which stands for Intellectual Property, refers to modules that have been previously developed by others, tested, and verified. We can be confident in their functionality. If you have a use case where you can leverage these IPs, you can save time and, in many cases, reduce costs by using them. ISE includes a large number of these IPs, and if they fit your needs, it's highly recommended to use them. As I mentioned in the previous slide, IPs are modules designed for common tasks. Because of this, there is a good chance that in a project you are working on, some of the IPs available in ISE will be useful to you. So, if there is an IP in the ISE software that precisely meets your requirements, the right decision is to use that IP to save both time and costs. Now, you might be wondering how exactly an IP can be used in a project you're working on. One important point to keep in mind is that in projects of medium complexity or higher, you'll typically need to divide your project into different sections. Each section is implemented separately as a module, tested, and once you're sure that the module is working correctly, you connect it to other sections. This is what we call integrating your system to achieve the final design. To do this, after you've partitioned your system into different modules, you usually write a main module, often called the top module. You then incorporate and connect the smaller modules within this top module to create the final complete module. As you can see in this diagram, a top module might consist of several submodules. Some of these modules, due to their specialized nature, you typically write using a hardware description language like VHDL or Verilog. For others, if a corresponding IP exists, you can use an IP from the ISE software. You bring these submodules together to build your overall system. Alright, let's look at a practical example within the ISE software to better understand this concept. We'll see where these IPs are located, how we can use them in our code, and how we can test them along with the rest of our code. To explain this further, I want to use an IP as an example, a simple one of course, within some code. To keep our example straightforward and focused on the main topic, I've prepared some code for you here. It has one input, which I've named input, and one output, which I want to be the square root of the input. Now, to design a module that calculates the square root of the input, one approach is to research existing algorithms for this purpose, then write the VHDL code for it, test it, and verify its correctness. This, of course, could take a significant amount of your time. Fortunately, one of the IPs available in ISE is the square root IP. Therefore, the wiser choice is to use this pre-designed and tested IP instead of spending time learning the algorithm, writing the code, and testing it. To use an IP, as always, right-click in the hierarchy section and select New Source. This time, instead of choosing a VHDL module, select the IP module. Now you need to give your IP a name. I'll call it SQRT for short, and then I'll click Next. On this page, you can see all the IPs that the ISE software offers. There are various IPs available categorized based on their functionality. For example, if you want to perform signal processing tasks, there are several IPs here that you can explore. For example, there's an IP for filters. Some modulation schemes have already been implemented and you can use them here. There are also functions like FFT, DFFT, and trigonometric functions that you can use. For example, we want to use the square root function, which you can find in the math functions folder under the square root section. For implementing the square root, the IP provided by Xilinx uses a well-known algorithm that you might have heard of. It uses the Cordig algorithm. With the Cordig algorithm, you can implement various trigonometric functions like sine, cosine, and many other operations, one of which is the square root function. So I'll select the Cordig option under square root, click Next, and finally Finish. For each IP, there is a wizard window which might have multiple pages. In this case, for this IP, there are 3 pages with various settings. Using these settings, you can customize the desired functionality for your specific application. As you can see, this window also includes a section called IP symbol, which displays the symbol or representation of the module you are customizing. There is also a tab called Implementation Details, which provides an estimate of how much of the FPGA resources will be consumed by this IP. In this page, you need to select the desired operation, and since we want to implement the square root operation, I'll select square root. This page also has some settings. The setting I'm interested in is the input bit width, which I'll set to 8 bits. The software automatically selects the output bit width, which is 5 bits. On the next page, there are some control signals that we can choose to include or exclude. For example, you can choose to have a clock enable for your module. If you do this, you'll see that the clock enable in the IP symbol section becomes highlighted, indicating that it's active. However, I don't need this option, so I won't select it. Now, if you look at the IP symbol, you'll see that my inputs are system clock, an 8-bit input for which I want to calculate the square root, and a 5-bit output that represents the square root result. Now, if I click the Generate button, this block will be created for me and automatically added to my project. If you want to learn more about the Cordig algorithm and how to implement the function it supports, and also gain more insight into how to configure the various parameters of this wizard, you can click on the Datasheet button at the bottom. This will automatically open the datasheet for this IP, where all the information you need, including how to configure the IP's parameters, is provided for you to study. Now I'll click the Generate button to create this IP and add it to my project. As you can see, the SQRT IP has been added to my project, and you can see it indicated by this symbol here. Now I need to add this IP to my main code, which I've named IP_test. To do this, I need to perform 2 steps. The first step is to introduce or declare this IP to this module. You probably remember from previous lessons that the place to declare signals in module is before the begin of the architecture, that is, in this area. After that, I need to use an instance of this IP in the system, or instantiate it. While instantiating it, I'll perform another operation called port mapping. Port mapping means specifying where the inputs and outputs of the IP or module I'm adding to my system should be connected. To do this, you can simply click on the IP, then at the bottom in the core generator section, click on the plus sign to expand it. Then double click on the last option, which says View HDL Instantiation Template. This will automatically generate the code you need to write. This part is the component declaration, which you can easily copy from here and, as I mentioned, paste it before the begin of the architecture. For instantiation, you can take this section, copy it, and, as I said, paste it after the begin of the architecture. You don't need to make any changes to the part related to the component declaration. However, the section related to instantiation and port mapping requires a couple of modifications. The first change is that this section starts with a phrase called a label. Before this colon, it's called a label, and you should give it a unique name. For example, I can name it SQRT0. After that, there is entity name followed by the keyword port map, and then you'll see the area where you can perform the port mapping. As I mentioned, port mapping means specifying which ports of the IP we are instantiating should be connected to which port or point in our main module. I simply want to connect the inputs and outputs of this IP to the inputs and outputs of the module I wrote earlier. Therefore, I connect the clock to the clock of the SQRT block. I connect my input, which I named input and is 8 bits wide, to the 8-bit input of the SQRT module. And I connect the output of the main module, which I named square root and is 5 bits wide, to the output of the SQRT IP module that I'm instantiating. You can also tidy this up a bit with a few tabs to make it clearer for when you want to read the code later. So what I've done is implement a square root module or SQRT using an IP. To add it to my project, I performed the 2 steps of component declaration and port mapping. For this, I used a feature provided by the software itself. I right-clicked, selected this option, and the sections I needed to add to my code were automatically prepared in this temporary file. I then copied and pasted these sections into the appropriate places before the begin statement of the architecture section for component declaration and after the begin statement for port mapping. After copying and pasting the section related to port mapping, I needed to connect the ports of this module to the appropriate points in my main module. For simplicity, I connected them to ports of the main module. Now we can test this module to make sure it works correctly by running a simulation. For simulation, the first step, if you remember from the previous lesson, is to create a test bench. So I'll right-click here, select New Source, choose the VHDL test bench option, and give the test bench a name. I'll name the test bench IP_test_TB. Then I'll select Next. Now I need to specify which module I want to create the test bench for. I want to create it for the IP_test module, so I'll select it. Then I'll click Next and Finish. My test bench has been created, and all I need to do is provide an input to the input port. As you probably remember from the simulation lesson, I can go to the section that says Insert a Stimulus here and assign my desired value to my inputs. In this case, my only input is the input port. I want to give it the value 16, so I'll enter the value here and save the test bench. Then I'll select the simulation option and click on my test bench. At the bottom, next to the ISim simulator, I'll click on the plus sign to expand it and double click on Simulate Behavioral Model. The ISim software is launched from within ISE, and you can see the results of this simulation. Now here we have the number 16 for input, and its square root, shown next to the square root output, is 4. To read these binary numbers more easily, you can right-click on these port names and select Unsigned Decimal from the Radix menu to view the numbers in decimal format. So this is 16, which we provided as input in the test bench, and this is 4, which is the square root of 16 generated correctly by our system, and you can see it here in the simulation. Finally, let's go over a few points to keep in mind when using IPs. The first point is that if any part of your system can be implemented using an IP, definitely do so, because using IPs saves both time and costs. The second point is that you usually can't implement an entire project solely with IPs. There will be many parts of the project that you'll need to code specifically. Therefore, the availability of IPs doesn't eliminate the need for HDL coding. And the last point is that Even if you sometimes have to pay for an IP, in many cases, using it will still be cost-effective. This is because the cost of a module is often much less than the cost of the time you'd spend developing and implementing the code yourself. Therefore, using IPs, even paid ones, is usually economical. I hope this video has been helpful to you and that you'll be able to use it in the design and implementation of your future systems. If you enjoyed this video, please give it a like, and if you're not already part of the community, hit the subscribe button and the bell icon to be notified each time I share a new video. Thanks for watching this video. I'm Ahmed Sagafi, and I see you in the next one.